Yesterday, April 21st, 2026, NASA held a press conference at Goddard Space Flight Center in Maryland. Behind the podium stood a completed space telescope, 42 feet tall, 14 feet wide, gleaming in a sterile white clean room. The NASA administrator looked at the camera and said this: "What would take Hubble 2,000 years to do, Roman can do in 1 year." The telescope is called the Nancy Grace Roman Space Telescope. It has been in development for 16 years. It cost more than $4 billion. And it launches in September 2026, 5 months from now. Its primary camera is 300 megapixels. Its field of view is 100 times larger than Hubble's. It will generate 11 terabytes of data every single day, more data in its first year than Hubble will have produced in its entire lifetime. During a 5-year mission, it will produce a 20,000 terabyte archive of the universe. One of the engineers said this about the images it will capture: "They will be so large there is not a screen in existence large enough to show them." Today we go through what this telescope is, what it does, why it is different from both Hubble and Webb, and what it is going to find, including things scientists openly admit they cannot predict. Stay with me. Who was Nancy Grace Roman? The telescope is named after a specific person, and understanding who she was makes the mission more meaningful. Nancy Grace Roman was born in 1925. She became passionate about astronomy as a child, organized a neighborhood astronomy club at age 11 in Nashville. She went on to earn a PhD in astronomy from the University of Chicago in 1949, at a time when women in science were actively discouraged and systematically excluded from most research positions. In 1959, she joined NASA as the agency's first chief of astronomy, the first woman to hold an executive position at NASA. She was offered the job and responded, "I jumped at the chance." In that role, starting in the early 1960s, she assembled the committees of astronomers and engineers that envisioned what a space-based telescope could do. She organized the scientific community around the concept that became Hubble. She set up the funding structures, the institutional frameworks, the scientific justifications. Without her work, there is no Hubble Space Telescope. She was called the Mother of Hubble. She died in December 2018, at age 93, never seeing the telescope that carries her name. The renaming from its bureaucratic designation to the Nancy Grace Roman Space Telescope was announced in May 2020. The telescope that will produce more data than Hubble's entire lifetime in a single year is named after the woman who made Hubble possible. That is the context. What Roman actually is: the numbers. Let me give you the specifications because the numbers are the story. The primary mirror, 2.4 meters, 7.9 feet in diameter, identical in size to Hubble's primary mirror, same collecting area, same sensitivity to faint light. But the camera is completely different. Roman's wide-field instrument is a 300.8 megapixel multiband camera covering visible and near-infrared wavelengths. It captures a patch of sky 0.28 square degrees in a single exposure. That is 100 times the area covered by Hubble's imaging cameras in a single shot. What this means in practice: Roman has Hubble's sharpness but covers 100 times more sky per exposure. What Hubble needs 100 exposures to cover, Roman covers in 1. The efficiency multiplier is enormous. The NASA administrator framed it this way: what would take Hubble 2,000 years to process, Roman can do in 1 year. The systems engineer at Goddard put it differently. In the first year, Roman will have sent down more data than Hubble has produced in its entire lifetime. Hubble launched in 1990. That is 36 years of observations, surpassed in the first 12 months of Roman's operation. The data rate, 11 terabytes per day, every day, for 5 years. Total mission archive, 20,000 terabytes. The Coronagraph instrument, a high-contrast imaging system that can suppress starlight by factors of up to 1 billion to 1. 1 billion to 1. This means Roman can block out a star's light so completely that planets, which are hundreds of millions of times fainter than their host stars, become directly visible. Roman will orbit at the Sun-Earth L2 point, the same location as the James Webb Space Telescope, approximately 1.5 million kilometers from Earth. It will launch on a SpaceX Falcon Heavy rocket from Kennedy Space Center in September 2026, under budget and 8 months ahead of its original schedule. How it is different from Hubble and Webb. This is the question everyone asks when a new space telescope is announced. We already have Hubble and Webb. Why do we need another one? The answer requires understanding what each telescope is designed to do. Hubble sees primarily in visible and ultraviolet light. It has a narrow, deep field of view, like looking through a straw at the sky. It is extraordinary at capturing detailed images of individual objects: a galaxy, a nebula, a star cluster. It has produced some of the most iconic images in the history of science, but its field of view is so narrow that surveying large areas of the sky takes years. Webb sees primarily in infrared. It is the most sensitive telescope ever built for infrared astronomy. It can see light from the first galaxies that formed after the Big Bang 13 billion years ago. Its field of view is also narrow. Webb looks deep into small patches of the universe with extraordinary sensitivity. It is a precision instrument for individual observations. Roman sees in visible and near-infrared, overlapping with both Hubble and Webb in wavelength coverage, but with a completely different philosophy. Roman does not look deep at small patches. Roman surveys vast areas of sky at high resolution. It is a wide-angle camera for the universe. A useful analogy. Hubble and Webb are microscopes. Roman is a census taker. Where Webb might spend 100 hours on a single galaxy to understand it in extraordinary detail, Roman will photograph millions of galaxies in the same time. Roman provides the map, the large-scale structure, the statistical patterns, the overview. Webb and Hubble provide the close-up detail within that map. The two approaches are complementary. Roman will identify thousands of interesting targets, unusual galaxies, unusual star systems, unusual transient events, that Webb and future telescopes can then study in depth. Roman finds the questions. Other telescopes answer them. The three missions. What Roman will actually look for. Roman's science program is organized around three large surveys, each targeting a different frontier. Survey 1, the High Latitude Wide Area Survey. Roman will map approximately 5,000 square degrees of sky, roughly 12% of the entire sky, capturing images of hundreds of millions of galaxies and measuring the distances to tens of millions of them. This survey is designed to probe dark energy and dark matter. Dark energy is the mysterious force driving the accelerating expansion of the universe. It was discovered in 1998, an observation that won the Nobel Prize in 2011, but its physical nature remains completely unknown. It makes up approximately 68% of the total energy content of the universe. We have no idea what it is. Dark matter is the invisible mass that holds galaxies and galaxy clusters together. It makes up approximately 27% of the universe. It interacts with nothing except gravity. It has never been directly detected. We know it exists only because of its gravitational effects. Together, dark energy and dark matter make up 95% of the universe. Everything we can see, every star, every galaxy, every atom, is 5% of what exists. Roman's wide area survey will use weak gravitational lensing, tiny distortions in the shapes of background galaxies caused by foreground mass, to map the distribution of dark matter across the universe and trace how dark energy has affected the expansion over 11 billion years of cosmic history. Survey 2, the High Latitude Time Domain Survey. Roman will repeatedly image the same regions of sky over time, watching for changes. Supernovae, exploding stars whose brightness follows a known pattern, serve as standard candles for measuring cosmic distances. By cataloging tens of thousands of Type Ia supernovae, Roman will measure the expansion history of the universe with unprecedented precision. This is one of the most powerful methods for constraining the properties of dark energy. Survey 3, the Galactic Bulge Time Domain Survey. Roman will monitor dense star fields in the center of the Milky Way at high cadence, watching for microlensing events, where a foreground star or planet passes in front of a background star and temporarily magnifies its light through gravity. This technique can detect planets that transit methods cannot, including planets in wide orbits, free-floating planets not bound to any star, and small rocky planets around distant stars. Roman is expected to discover more than 1,000 new exoplanets through microlensing alone. The Coronagraph, directly imaging other worlds. The second instrument on Roman is the Coronagraph, and it represents a technological leap that has direct implications for the search for life. Directly imaging an exoplanet is one of the hardest problems in astronomy. A planet orbiting a star is like trying to photograph a firefly hovering next to a searchlight from 10 kilometers away. The star is billions of times brighter than the planet. The planet's reflected light is completely overwhelmed. Current coronagraphs, instruments that block starlight, can suppress stellar light by factors of around 100,000 to 1. That is extraordinary. Roman's coronagraph can suppress starlight by factors of up to 1 billion to 1. That is 10,000 times more powerful than current space-based coronagraphs. At that level of contrast, planets that are 100 million times fainter than their stars become visible. Gas giants around nearby stars become directly imageable. And with spectroscopy, analyzing the light from those planets, their atmospheric compositions can be measured. What gases are present? Whether oxygen, water, methane, the chemical signatures of life are detectable. Roman's coronagraph is designated as a technology demonstration. It is not the primary science instrument, and it will not be used for the large surveys. But the data it returns will validate the coronagraph technology that will be central to future missions, specifically designed to search for biosignatures on Earth-like planets. The roadmap from Roman's Coronagraph to the direct detection of life on another planet is long, but Roman is the next step on that road. The unexpected. I want to close with something the senior project scientist said at the press conference yesterday. Julie McEnery, Roman's senior project scientist, was asked what she was most excited to see from the mission. Her answer, "I very much hope, and in fact expect, that the most exciting science from Roman is going to be the things that we didn't expect, that we couldn't predict, but that will set the new deep questions for future missions to address." That statement deserves attention. Hubble was designed to measure the expansion rate of the universe. It did, and the answer was so unexpected that it revealed dark energy. Hubble was designed to study stars and galaxies. It did, and in the process showed us that nearly every large galaxy has a supermassive black hole at its center, something nobody had anticipated at Hubble's launch. Webb was designed to see the first galaxies. It did, and found galaxies so massive so early in cosmic history that they challenged the standard model of structure formation. Every major observatory in the history of astronomy has produced its most important discoveries in areas nobody anticipated. Roman will map more sky at higher resolution than any telescope in history. It will generate more data per day than Hubble has in 36 years. What it will find in that data, what patterns, what anomalies, what objects, what phenomena, is genuinely unknown. The scientists who built it expect to be surprised. That is not humility. That is the honest assessment of what happens when you open a new window on the universe. Roman launches in September. We will be covering it. The Nancy Grace Roman Space Telescope was revealed yesterday. Fully assembled, 42 feet tall, launching in 5 months. 100 times Hubble's field of view. 11 terabytes of data per day. 20,000 terabytes over the mission lifetime. A coronagraph that suppresses starlight by 1 billion to 1. A census of 1 billion galaxies. More than 1,000 new exoplanets through microlensing. A three-dimensional map of the universe stretching back 11 billion years. Named after the woman who made Hubble possible, built to do what Hubble cannot. Subscribe to follow the launch in September and the first data releases, and tell me in the comments, what do you think Roman is going to find that nobody expected? Because if history is any guide, the answer to that question is the most important thing it will do.